Hello, everyone. Welcome to Science, the Big Questions panel. A panel that, when I took it on, I thought it was going to be quite easy, like the Sunday morning way that Nicky Campbell attempts to answer fundamental questions with an audience full of uniquely unqualified people, and Kevin Fryery quite often. But it turns out that this is a much more difficult panel because of the nature of a big question of science, which we may get into. But to help me, I have some actual scientists with me, which I should start by introducing politely. Perhaps we can start with Jeff. Just perhaps if you could explain your specialisms and maybe what you would consider a big question of science.
Okay, yeah, so I'm Jeff Forshaw, and I am Professor of Particle Physics at Manchester University. So my main interest is in theoretical particle physics. So you might think that I would be trotting off all the big questions as the typical questions in particle physics, the big fundamental questions, and I could do that, but I won't. So
See what I mean?
It depends who's asking the question, really. And like, what do you want? What do you want from the list? So here's a list of big questions, and I think it could be a dangerous thing to do, right? If you're talking to politicians, I mean, the idea. I mean, it's very different to say what's a big question, and it's certainly not the same as asking people what they should work on. A scientist or academics in general, should they work on big questions, or should they work on things that are really interesting to them? So I think big questions are extremely subjective, and answering the canonical big questions like global warming very often, I think, involves solving lots of little questions in practice. And often you don't know what the little questions are that are going to unlock the big questions. So in a sense, the little questions, the big questions.
Helen?
I'm Helen Czerski. I'm a physicist, but a different sort. I do bubbles, so I do the little things at the bottom of the big picture. And I think the thing I'm glad that I'm not the only one, because when I was asked and Rick asked us to do this panel, I sent back this email going, well, I'm not sure about this big questions thing. Clearly I wasn't the only one. So the thing that bothers me about the big questions is the sort of glorification, like Jeff said, of some questions above others. And there's this sort of artificial hierarchy. And that's not how science works. Science, the structure of scientific knowledge, if you like, is sort of quite flat. There are some things, Newton's laws of motion, that unless you're doing very weird things, apply most of the time, and you could call them quite fundamental. But then a lot of the way things work in the middle is messy and difficult, which I'm sure we'll come on to. And so this whole idea of there being big questions in science it's too easy, I think. So I think, the big questions are the only definition I think that matters is probably that they're the ones no one's asked yet. But I'm sort of suspicious of this idea that some questions are... I think you've got to question why you want some questions to be more important than others. And sometimes they are. It's not that some questions aren't more important than others. It's just that you've got to be clear about why. And that's not always... It's not always as straightforward as everyone thinks. It's difficult, right?
Tim.
Hello, I'm Tim O'Brien. I'm a professor of astrophysics at Manchester. And I work at Jodrell Bank Observatory, so I'm an astronomer. So there are a number of big questions in astronomy, and some of them I'll be talking about in my talk after this panel. But just to take that theme, I like to quote Donald Rumsfeld, because who doesn't? Because if you can remember, those of you who are a certain age, Donald Rumsfeld was rather taken to task for a strange phrase that people thought was strange, and in fact is not strange at all. It's a real thing, and he talked about the known knowns. So there are things that we know, and then there are the known unknowns. So there are things we know we don't know. So those are the questions. There are questions that we can list in science, and there's many of them, as we've just discussed, that we know we don't know the answer to, and we'd like to know the answer to. But then the third part, which is what perhaps where it seemed to get silly, but it certainly doesn't, is the unknown unknowns. So there's these three classifications. The things you know you don't know, but then there's the stuff you don't even know you don't know. And I think that's often where the real excitement comes, and it's very difficult to even ask those questions, of course, at the moment. So those are really big questions.
So we were lucky enough to have Jeff come and give the Manchester Skeptics in the pub a talk recently. And there was a couple of interesting questions that came out about that, in particular questions related to discoveries around the Higgs field and the discovery of the Higgs particle, which I suppose is a confirmation of the Higgs field. And you mentioned a question that I suppose hadn't occurred, which is you were talking about the peculiarity that the Higgs field is not causing a universe to continue expanding as it has done. Could you expand on that?
So, I was talking about, the talk was mainly about early universe cosmology and the fact that there is a good deal of evidence now in support of an idea, well, it's more than just an idea, called inflation, which supposed that in a sense, before the Big Bang, the universe was expanding very, very rapidly as a consequence of vacuum energy. So there was some energy in empty space which was driving this rapid expansion of the universe, some field which was permeating the whole of space at that time. And that rapid expansion finished, and that field essentially converted into a hot, dense gas of particles, which we now think of as the Big Bang. So it did it actually through a phase where the entire universe became filled with what's called a Bose-Einstein condensate, which means it was cold. It was a cold gas of heavy particles just before it became a hot gas of light particles, and that hot gas of light particles then went on to make all the stars and galaxies and people and things. So that's the backdrop to all of this. But key to the idea of inflation is the idea that this vacuum energy was driving this rapid expansion, and it was the physics of that field which led to the hot Big Bang. But just taken at face value, we know a similar thing that's happening now, which is that the empty space is filled with the Higgs field. The particles associated with it have been produced at the Large Hadron Collider. So empty space is filled with this field, this kind of cosmic treacle, and it's that which gives the appearance of mass to the elementary particles. So it's a very important element of the standard model of particle physics, and already, so Peter Higgs has got the Nobel Prize for it in after its discovery in 2012. So it's established that this Higgs field exists, but it's not causing the universe to explode now, really rapidly. So there's something which we're not understanding. So the vacuum energy associated with the Higgs field appears to be very close to zero for some reason. It's one of these things that we can't calculate. We can't calculate what the vacuum energy should be. So it is possible that it could be zero or very close to zero, and consequently there's no rapid expansion in the universe. But it would have to be exceptionally close to zero for that to be the case. So, and naive theoretical predictions predict that it should be hundreds of orders of magnitude bigger than its observed value, because we do actually measure that there is a small amount of what looks like vacuum energy causing the universe to accelerate in its expansion. But it is literally hundreds of orders of magnitude off the naive theoretical expectation. And that is, I think, a lot of theoretical physicists, me included, regard that as the biggest unsolved problem in fundamental physics, in elementary particle physics and cosmology. Like, what is going on with vacuum energy? And it's crucial because we've got the Higgs field, which in principle contributes to vacuum energy, and we've got this theory of inflation, which successfully predicts how the galaxies are distributed across the sky, and it predicts the cosmic microwave background radiation very accurately. So it's actually been really successful, this theory of inflation, so people take it really seriously. But not everything holds together for the reasons I've just said. So nobody really has come up with any kind of a good answer as to how to correctly calculate vacuum energy in fundamental physics.
So you mentioned there a mysterious force increasing the expansion of the universe, which I think is what Tim may talk about a little later, right? But colloquially referred to as dark energy.
I'll touch on it, yeah. And it's, when we're giving it a name, we're good at giving things names, even if we can't actually calculate them. But we only called it dark energy because there's this other thing that we didn't understand called dark matter. So it's just got the same name, but it doesn't help us understand what it is. I'm sure it is one of the biggest questions, yeah.
And so you use the term vacuum energy several times. Obviously, energy is a big question from an engineering point of view, right? And I know when we discussed this panel, Helen, you gave me questions which I dismissively described as engineering and technology questions.
Yeah, I made a face about that.
Yeah. Of course, I'm quite right to, because it's, the two are really the same thing.
Well, I think, there's it's a very complicated subject, but it seems drawing the question away from the obvious big questions matters quite a lot. So on the subject of the physics, for example, there's a lot of big questions, that you can name that are known unknowns, if you like. There's a force or a type of thing, a category, something that might fit, depending on what it turns out to be, into a nice tidy slot. But actually, I think some of the biggest research questions today are about messy things. So the sorts of situations here, this is complicated, the sorts of particle physics and cosmology that my two esteemed colleagues are far more qualified in than I am. They're extremely complicated and difficult, but relatively speaking, in terms of the number of things involved, compared with the world that we live in, they're relatively simple. A relatively small number of forces. I'm probably going to get shot down for this. Relatively small number of forces are involved, and actually, I think a lot of the questions certainly in physics, which are not being answered, are to do with the complex world we live in. And the reason it's more complex is that all forces are present in all situations, but there's a hierarchy of which ones are important, right? So if you're dropping an apple from the top of the atmosphere where there's almost no air, gravity is the dominant force and it's going down, and you can just worry about gravity. But if you're, out on the ocean where I work, or you're somewhere in the middle of a hydrothermal vent, for example, there's lots of competing forces. There's surface tension and viscosity, and gravity matters, and maybe there's sort of electric field set up somewhere if you're not in the ocean. There's all these competing forces that are all present, and it's not like there's a clear hierarchy. They're sort of they're generating a complex system because they're playing off against each other and interacting in quite subtle ways. And the problem with that sort of question, which is basically how does this system work, how does the climate work, for example, is that there are big models of it that look quite simple, but the problem is there's no simple answer. So the nice satisfying thing about what Jeff was describing, for example, is that if you find that, it depends what you find, but it could be like finding the Higgs boson, right? It's that there it is, we've found there's a thing in that box and we've found it. Whereas when it comes to the question of how the climate works, it's like, oh well, we understand it a little bit better than we did before, but there's no sort of a eureka moment where we go, right, now we've got the answer, this is everything. And the problem is, I think, that when it comes to a lot of the sort of practical questions, and how our climate works is beyond the practical question, it's part of our life support system. There isn't a nice simple answer, but I don't think we should dismiss the question because it's not going to give us a nice little sugar rush when we get tick box, now we've found it. It's just an ongoing slow process of discovery, and I think questions like that get discounted because we know there's not going to be a hit at the end. We know that it's not going to happen. It's just going to be, it's got 1 step forward, 3 steps back, 1 step forward. And I think those are very important questions, and often they relate to the structure of our society, and the sorts of questions that Rick's referring to are sort of how do we deal with our world? How do we manage energy distribution? How do we manage our resources? What do we do when if we find out anything about how our brain works? What consequences does that have for ethics? They're difficult, and they're not nice and tidy, and they're not, tick box, hooray for us, gold star, move on. But I don't think we should be afraid of addressing them. I think they're the really big questions.
Yeah, can I add to that? So I'm definitely not going to shoot you down, as you right. So I agree that. So when I was talking at I think I mentioned this when I was talking at the skeptics meeting last week. It's understanding the world now that's difficult. Not understanding it at the time of the Big Bang. The calculations at the time of it sounds a bit weird, but the calculations that you need to perform to understand the universe when it was essentially a nearly uniform plasma. really easy. And it was a weakly interacting plasma as well, even right back to very early times in the universe's history, when an entire observable universe could fit in this room. The calculations then, which I teach, or used to teach, to our fourth-year undergraduates, they are significantly easier than trying to understand what happens, and quite similar, in fact, this is why I'm making the analogy, to what happens if you kick a bucket of water. So you get a tank of water, kick it, and try and understand how the waves move around inside that box. That is a far more difficult problem than having that plasma in the early universe and then hitting it and causing waves in the plasma to move around. The plasma waves are much easier to calculate. So what we're trying to do with fundamental physics, like particle physics, like ticking these boxes off, is trying to figure out the rules to a game. So it's really very similar to what you might do if you were watching people play chess, and you were trying to work out what the rules to the game of chess are just by watching them. And in a sense, particle physicists are doing that with nature. They're trying to figure out what the fundamental rules are that give rise to the game. Right? But what Helen's talking about, the complicated stuff, that's the stuff where you get to watch Garry Kasparov playing a brilliant game. You know, knowing the rules of chess is not the same as being able to play like Garry Kasparov. So in a sense that, you know, particle physicists, I think, know their limitations, right?
I've never been compared to a world champion
they
chess
are
player
solving.
before. I'm feeling quite good about myself here.
So just trying to figure out the rules of the game, actually understanding what the consequences of the rules are, is where a lot of the fun is. I mean, I enjoy trying to figure out the rules, but I also I enjoy messing about with trying to understand the messy consequences as well. I mean, in a sense, a lot of the beauty, that's where the beauty of the world is, in large part.
So I used to assume that one of these big questions that could be answered quite easily with a checkbox, as Helen was describing, would be whether we were alone in the universe. But it seems to me, actually, I've come to realize that if there is intelligent life, our discovery of it or apprehension of it is actually probably going to be a very slow process of suspecting for a long, long time. What do you think, Tiana? And listening on a giant telescope must give you the best chance of...
Maybe. I think it's... I mean, I take on board everything that Helen and Jeff's been saying, but I mean, there are still these big questions, and I think...
Well, you look at the cosmos, you've got the best justification for looking for big questions. As good as it gets, right?
Answering the question whether we're alone in the universe has to be a big question, right? Because it would, you know, I think it would change a lot of people's ideas about the way they live, really. Maybe even our life here on Earth might change if we were to understand that we were alone. And if you think about climate change and we think about looking after the planet, the fact that we, you know, at the moment we are alone, we don't see anybody else out there coming to help us, you know, to fix these problems we've got on the planet. So I think thinking about those big questions, the Earth as a sort of spaceship, if you like, you know, in the universe, sort of with its own resources and so on, I think is challenging. But whether there's life elsewhere, I mean, we pick up signals all the time. We pick up signals that we don't understand all the time. So sometimes people ask me, have you ever seen anything you don't know what it is? Yeah, every day. We'd look at our signals with the radio telescope every day and see things we didn't know what they were. And that's generally, I would say, true for most scientists. If you look at your instrument, there'll be something that you didn't immediately understand, and then you have to try and work out what it is. In our case, if we're talking about signals from extraterrestrial civilizations, we'd be talking about technological signals. And our big problem is that we produce many technological signals here on the planet. And so it would be a matter of sifting through the signals and distinguishing ones that are being produced either here on the surface of the Earth or perhaps from orbiting spacecraft, distinguishing those from ones that are coming from extraterrestrial civilizations somewhere. It's certainly not impossible that we would pick up such a signal. We haven't yet, despite what some people keep claiming. We're not keeping it secret. We would tell people, particularly after we checked that it was right. I wouldn't be tweeting that we'd found a signal from extraterrestrials before I was sure that we'd done so. But as it stands, we haven't. And actually, that's one of the biggest questions: is why haven't we? Because if there is life elsewhere, in principle, it's technologically possible now for us to travel across the galaxy, to build spacecraft that travel across the galaxy, maybe even people, if we could be bothered to put enough time and effort into it and money. So the question is, why haven't why haven't the aliens? Why haven't they visited here? That would be a sort of an important question to ask, I think.
And there's been lots of recent developments in the discovery of exoplanets, and there was in the last few months there was that planet that had some kind of occluding structure being detected around it as well. But there again,
Tabby's star, it's called. Yeah.
That's right.
So just to explain for those people who didn't see it, there's these little dips in the light from the star, and this is one of the trivial ways of discovering something new. Let's just go back to this topic of how we work out what a good question is to ask, because when I started my PhD in the mid-1980s, I still have the list of all the PhD students in astronomy who were beginning that year and what topics they were working on, and not a single person was working on planets orbiting other stars. Not a single person in the mid-1980s. It would have actually been regarded as a pretty weird out there topic to be working on, thinking about finding planets orbiting other stars, whereas now it's one of the biggest areas in astronomy are these exoplanets, and that's in whatever it is 30 years or so. The situation has changed, so things come up, and it's trivial to detect planets orbiting other stars. You can do it with a telephoto lens on a camera. In fact, it has been done. You look at the brightness of the star, it dips regularly as the planet goes around it and blocks the light from the star, and you see this regular dip. So in fact, the technology required was not complicated to do that, just nobody had really thought of doing it. Perhaps we needed the computers to do a lot of observations, a lot of calculations. But yeah, Tabby star's the one that has this weird stuff, and almost certainly not an alien megastructure orbiting the star, but yeah. But
that was the speculation, yeah.
Yeah.
And of course, that's interesting because it tells you that, us discovering something like that is going to come as a very long process of trying to rule out any other alternative explanation, and it could be difficult or near impossible.
But what we're looking for in that case, that's interesting. It's interesting as a big question because what we're looking for is also influenced by us. And you're talking about technological stuff, like detecting signals. There's a great quote somewhere in the Hitchhiker's Guide to the Galaxy that man thought he was the most intelligent species on planet Earth because he'd invented wheels, the engine, computers, and so on. Whereas all the dolphins had ever done was muck about and have fun in the ocean. And the dolphins thought that they were the most intelligent species for exactly the same reason. So there is this thing that's an interesting question because you have to make assumptions when answering it. And the problem is that there are unknown unknowns about what it might look like. So how do you go looking for something? Not only do you not know whether it's there, you actually don't know very much about the parameters about what counts. And maybe, you know what, there is life. It's hiding under a rock and it's quite happy. And it's not,
I mean, a good example of that, just, as an actual example of this, just in recent years, is a phenomenon called fast radio bursts, which are very brief flashes of radio waves coming from all over the sky. They only last a fraction of a second, so it's and off again. Really bright. They're really bright things, actually. But because they only lasted a fraction of a second, we'd never noticed them. And we only noticed them in recent years. They would have been in all our data since we developed radio telescopes in the 1940s. But because we hadn't looked at the data in that way, we hadn't seen them. And I think that's an interesting, like you say, we don't know what to look for when we're looking for alien signals. I don't think those are alien signals, by the way, but yeah.
So I've got a question that I'm just saying to be provocative. That's always bothered me about big questions, which is that, I am obviously saying this from the point of view who studies the ocean and atmosphere and the Earth's engine, right? Biased. So, but here's the thing. It's always struck me, so wherever the vacuum energy is coming from or whatever it is, the answer to that question is going to be the same in 20 years' time, we assume, because we assume the laws of physics are invariant. But then when it comes to how the Earth's engine works, the answer to that question will be different in 20 years' time. So here's a big question thing, is do you prioritize your big questions by whether or not, whether they're going to change? This is an earth scientist thing, on the days when they get a bit bitter. It does happen. There's a lot of money goes into these questions, and it's brilliant. This is a great thing. But in a world of limited resources, do you focus on the things which are going to have practical, implications now? And obviously we need, we're a species. It's curious. It's interested. We want to be exploring. But it's like going off exploring when you've not done the washing up, So I don't know, but that might feature in the definition of a big question. It is we always have to decide. It's one of the boring things about living in on a finite planet with finite resources and finite lifespan, you have to do some things before you do other things. So does that matter in your big questions definition? Or are you just going to not do the washing up?
Well, the other sense in which science questions are big is, I remember when I was being interviewed for university, I was given a photocopy from a New Scientist magazine, which was describing the building of the LIGO observatory, which only in the last 12 months has yielded positive results of detection of gravitational waves. Again, this is another area that I don't talk about for fear of ruining Tim's talk later. But this is a very long-scale project, long-term project. I suppose for LIGO, it's down to the incredible precision that experiment has to be performed with. The LHC, an enormous science project, and at vast cost. So it seems to me a lot of these questions are big in the engineering that has to be done in order to answer them. Which obviously raises a question about funding and gets back, I think, to what you were saying, Jeff, about who is asking the question and how do you provide the answer.
I think Helen's question is an important one because it is the question of with limited funds, what should you do? Right? But I wouldn't pitch it quite the way that I wouldn't put it in the way that you did. I think that it's okay, you could stop doing particle physics. You could stop doing that, and you could focus on the washing up instead. Right? But you could do both. Right? You could argue that this stuff is so important for society that it's other things that should take the hit. That you shouldn't be turning off the LHC in order to do more work on climate change. I think that's. I just think that would be a mistake. I think you should do both because. I don't feel that I need to defend why it is that it's important to have the Large Hadron Collider. We could talk about that, right? But I think from a cultural perspective, I am defending it now, aren't I? So let me not do that. I'll stop. That's what I think. I think that we should be arguing strongly that we should do both, and it isn't. Sometimes it is set up in a way that it makes it look antagonistic, like we are doing the fundamental things and you're just doing the washing up, right? But it shouldn't be phrased in that way.
No, it's certainly possible to do both, and you wouldn't have people could have asked why you sending rockets into space, at the time they were done, and there was particular reasons for doing that perhaps in the end turned out not to be the reasons we use it now, and they're fundamental to understanding climate change, having spacecraft observations. That's despite what Donald Trump thinks.
I think what's essential. I would go further. I don't think it's a luxury. I think this is essential for our society that we've got scientists following their curiosity, right, in an unfettered fashion, right, as much as is possible. So you have to any influence from government should be more like a light touch on a rudder than somebody coming in with hobnail boots and saying you all have to work on this, right? Because that's not how creativity operates in science. You can't tell people what to do. It's far more effective if you let people have free rein. And so this thing about the unknown unknowns. The classic example of that would be something like quantum mechanics and the work of like Werner Heisenberg and Schrödinger in the 1920s and 30s and Dirac. They were working on stuff that nobody even knew that was something to work on, right? And then by 1950, people at Bell Labs had invented the semiconductor transistor, which is now in its billions on everybody's phones. It's completely transformed the world, and you could make a case for arguing that it's the most important technology of the last 100 years or so. That came out directly out of an unknown unknowns thing, right? So anybody who would be thinking of edging the bets at that time and saying you should work on this, you should work on that, they wouldn't have said to Heisenberg, "Oh, you just carry on doing that thing that nobody has any clue what you're doing because you just make." That's a really good example of just somebody being curious and, in consequence, doing something that changes the world. And the stakes are too high. Right?
And I guess you have to accept that
there are not that many scientists around, right, thinking about new things. And it's the rare fluctuations. It's the one or two that come along every 20 or 30, 40 years who change the world. So you're kind of hedging your bets and saying, you just work on whatever you want to, right? And let's see what happens. And it's demonstrably been the case that that's been effective. And I think steering science and scientific research and trying to kind of preempt what's important and what's not important, I think that's a disastrous road to go.
What about when there are? So I am being deliberately provocative here, but someone has to be. So there are.
No, you don't.
I thought this whole thing was about asking questions and pushing people out of their comfort zone and stuff. So, for example, in the high Arctic in the next 20 years, we are basically in danger of World War III, and I'm actually not joking. Canada and Russia and America, like as the ice clears and trade routes start to cross that region and resources become available that were not previously available, we risk a global disaster if anyone generates an oil spill up there. There are these enormous political consequences, but the only way we can preempt the political consequences is to do the science to understand what's going on. And I would argue that that's a place where understanding the Arctic, yes, there's curiosity-driven science, and obviously not arguing against that, but in this case there is an enormous political reason, because if there has to be a battle over the Arctic, and there will be, in 20 years Arctic geopolitics is going to be on the front pages almost every day, then you want it to be based on knowledge, and that's only going to work if we start acquiring the knowledge now, and doing that is a pragmatic decision. It's not obviously Earth atmosphere scientists would go poking at anything, but we're tending at the moment to go poking at the Arctic. First of all, because it's interesting, because it's changing so quickly that if we don't study it now, we won't have the science in 20 years' time. And secondly, because we can see what's coming down the line. Putin is an oil man. North Russia, full of oil reserves. Ships are starting to trade now through the Arctic Circle, and control of that space is going to become a gigantic issue. And prediction, being able to predict what might happen when and if things go wrong, is based on science which we haven't yet done. And so I do think there are pragmatic cases where the science does have to follow the political and the social situation on the ground.
I think that's certainly true, right? I mean, whether you like it or not. I mean, Los Alamos was a good example of like a political target, which where the scientific community was mobilised, and climate change and antibiotics. There are problems which are urgent and which consequently require urgent attention. Right? So that's notwithstanding everything else that I said. So I mean, those urgent projects exist and should be prioritised. And I think to a certain extent they are. But it's up to people to make that case, isn't it? To make the case that you just made now.
It's often a hard case to make, actually, because of the complication thing. It's quite easy in some cases to say to a funder, and I am caricaturing this, but with some funding agencies, you do wonder whether that's the way things get done. It's sort of cartoon style. But here's a big thing, we can find out a big thing with lots of impact. They like the word impact. Or here's a sort of complicated story that's got lots of jigsaw pieces, and we're going to do this jigsaw piece, but we're not quite sure whether it's going to fit in or whether it's going to matter at all. And it's a lot harder to make that case because it's complicated, in that the funders and the governments have the same problem as everyone else, which is that they want the instant hit. And actually the most important answers to a lot of these questions come out of, and it is following curiosity, but it's also just following the science. There's these jigsaw pieces, and we don't know how they fit together. But unless we identify the jigsaw piece, we're never going to know. But it's very hard. It doesn't sound very shy. It doesn't sound very exciting, which is one of the reasons for my skepticism about the idea of big questions, because I think it prioritises certain areas of science, and there are some much more sort of foundational things which sort of get left behind because you can't say, so I'm going to the Arctic next summer, spend 2 months on an icebreaker to study bubbles in between bits of ice. It's a mechanism, there's a mechanism there, we think if it's happening, it's very important, it's due to bubbles, ice shifting around, quite small scale fluid dynamics. You know what, I might go, and it might not be happening, right? We've seen some evidence for it, but I might go and it might not happen. It's going to cost a lot of money for me to go and do this experiment, but if I don't do it, we'll never know. And if I do find it, it'll plug into something, but we're not quite sure yet. There's a lot of people that think this is important, but we might all be wrong, right? And that doesn't sound quite as, I think there's a problem in the prioritization of science, in that everyone likes doing the things, the elegant things. And I think a lot of the complex science in the middle is not elegant. And so we've sort of got a problem, because if you can't make your elevator pitch, you've got a problem.
But you've got the funding for that, right? So you did get the funding for that.
I'm still waiting. If anyone from NERC is in the room, it's in your pile now.
So you've had to make that case, and
So there's 2 stages. I've got the first stage, but not the second stage.
There's an interesting kind of development in physics, though, that's been taking place over the last, say, 10, 20 years, which is a shift to working on more complicated problems, in part due to better computing resources, so it makes it possible to answer some questions that were just too difficult to answer before, and also developments in theoretical physics, so developments in information theory and complexity theory and nonlinear physics, which are making it more interesting. So this, like, the idea of a kind of a market in ideas, and people will work on what they find most interesting. I have faith that will draw people into the areas that you're talking about, because I might be misplacing my faith, just like free market economics is misplaced. Right?
Complex system, that you see.
But I'm optimistic that younger people who are not always going to be drawn into working on projects like the fundamental problems in cosmology and particle physics, and will be drawn more into these messier problems.
And
I
will say that. So I interview a lot of scientists as part of what I do for the BBC, and I ask. There's a few questions. You're getting to know people at the start. You have a chat. Did this with Tim a few weeks ago, and you say one of the questions you ask is, how did you get into science? And across the board, whatever subject they're doing, whether it's biology or semiconductor physics, 1 in 2 answers among more senior scientists is still Apollo. Even now, and there's they might be studying bat acoustics, but Apollo had something to do with it. So I do think that there's a role for those things that are just civilizations, things, seeing what a civilization is capable of, that draw people in. And then even if they end up in a different area of science, you've sort of... I've been astonished by the number of people who... Because I'm too young to remember the moon landings, right? So I don't have any empathy with that, because when I grew up, it just happened. Shuttle took off, came back, and he was like, well, there it is. Didn't really pay any attention until it stopped, and I watched that Nature video that had... if you've not seen this, go and find it. There's a video that Adam Rutherford, who was working at Nature at the time, made, which was... It followed an entire shuttle flight from takeoff to orbiting to landing, but every single shot was a different flight. So the first one was the first shuttle taking off, and then they edited it so that on the last day, the touchdown was the last ever shuttle to fly. And it had Challenger and Columbia, and it was a beautiful thing. And that was the first time I appreciated the shuttle program, just as it finished, because of that video. So the thing that there's also a question is part of the reason for answering the big questions, not just that as a civilization we want to and we should and we can, but that actually the inspiration we get from doing it is so great that you get a whole generation of scientists just from that.
You also get the techniques and the skills and everything else as well, because all these big questions, they draw you in. They do draw people in. They do draw young people in. They're interested in dinosaurs. They're interested in space. These sorts of big things pull people into science and technology. There's no way they're all going to work on the Large Hadron Collider or whatever it might be. So, but actually, they become mathematically literate. They become technologically competent. They get the computational skills. These big, our big project at the moment that we're working on is designing what will be the world's largest telescope, the Square Kilometre Array, which is going to be built in Australia and South Africa. Colleagues here in Manchester have been designing the networking systems that will carry the data around between these hundreds, and in the end, in fact, already thousands of antennas in the Australian and South African deserts. The amount of data being transferred on that network is 10 times the global internet traffic at the moment. So the amount of bits per second having to flow around this network and be dealt with by the computers is remarkable. So the skills required to do that are completely transferable, and can be applied to many other areas of economic activity. So I think there's lots of ways in which these sorts of topics are useful beyond the thing that Jeff started with the curiosity leading to the advances and not being able to predict them in advance.
That leads to something really interesting though, because my first thought when you said that, like, great internet fun, like massive terabytes going everywhere. Yeah, and you know what? There's bits of the South Coast where you can't get basically dial-up. And that does lead to this interesting question of the questions that you ask. Is this an elite thing to do, or do we involve everybody? In the sense of, it's all very nice. Like, so I this time No, a bit earlier than this time last week. I was running a half marathon to raise money for Yemen, the huge humanitarian crisis there. There's cholera. Cholera was solved as a scientific problem 150 years ago. We haven't got rid of the people problem yet. And so it's great to talk about going to Mars, but there's people dying of cholera, you know. And there is also this question with the big questions is that can you frame your big questions so that they relate to all of humanity? Or is it just, you know, for the people who are lucky enough to have time to think about them? I don't know. I think that's a big thing in science. What science should aim for, and what science should be, you know, how it should be organising itself. Like there are these great, you know, these. It's the same. No, there's always the thing. It's the washing up's always the boring bit, right? And how much you say, well, we ought to sort out the washing up before we do other things, and how much you just go. The inspirational value of this question is so great that ultimately we think it will help. You know, people who do not participate in our society because they're not privileged enough. So
in South Africa, for example, and in Africa more generally, these projects are being supported by the governments because of the capacity to build capacity within that country. You know, to draw people into education, into science and technology, because and they can you know, and they're owning those projects, you know, in those countries. So I think you can do both. Yeah, and I think you can do the big things and they can be useful to broader society.
Some of these big science projects are international projects as well, aren't they? So they do involve a large fraction of the world. And the way in which they're inspiring schools around the world, so reiterating what Tim said, I think that's not to be underestimated.
We've got to do all of it, haven't we?
Yeah.
The way the sense that you're giving me, Helen, though, is particularly areas like climate science is obviously got a strongly sort of political angle to it. Maybe it's easier to sell very pure science at the fundamental ends of the scale rather than the intensely politically kind of encumbered bits of science.
So that's inevitable, right? Because we're humans, and the best thing about the best thing about being human is the same as the worst thing about being a human, which is that you've got all the flaws of a human. And so I don't think you're ever going to get away from that. There's no point just saying, well, people shouldn't think like that, because that's what we think in terms of stories. That's how humans have communicated for years. We think in terms of stories. We're going to go with the story. We want a hero, whatever type, whether the hero is vacuum energy or whether it's another civilization. Like there's always, you know, our minds want a hero, and we're kind of stuck with that. And it's not that I want to be the wet blanket in the room at all. It's just that I think that the definition of this is where the problem comes with the definition of a big question, is that if you set out that framework, you've already picked the winners. And that's the dangerous bit. And it's going to happen a little bit, but if you're aware of it, you can just see it coming. And it's just that the world's a bit more complicated than that. And, you know, it's just, yeah.
Maybe somebody else, maybe you know. So when I think about the areas of science which are being funded, and what about research into curing cancer and climate change and antibiotic research? How much money is actually being spent on research into those areas compared to the Large Hadron Collider? I mean, my guess would be it's significantly more than so maybe we have.
Sorry, which one is significantly more?
Cancer research, for example.
Yeah.
And I don't know, climate change research, I don't know, but there are certainly a lot of very good people working in climate change. I don't know how the money that we invest.
Yeah, I don't know what the numbers are.
So
it's all very small, though. I saw that, you know, is it Andrew Steele's got that, what's it called? Someone in the room will know. That thing about making statistics into sensible numbers that you understand. And I think that the amount that the UK spends on cancer research per person per year is £1.60. And these are not big numbers. Whatever the comparison is, none of them are big numbers. And I'm not trying to set up a competition here. I just think these are questions that should be asked. And it's not asking the question, which is the problem, not having an answer.
Speaking of asking the questions, I think it's time we allowed the audience to ask some. But obviously, we spent quite a long time figuring out what is a big question. So, remember that it needs to have a question mark at the end. All right, I'm going to throw to the person nearest. And you speak in the top of it. Apparently, I've never used it.
I heard Helen talking the other week about static electricity, and we don't understand it.
We're getting better at it.
And I wondered if there was other things that everybody thinks we know. That actually, no, we haven't got a clue how that works.
Well, here's the thing, right? There is a difference between not having a clue and not knowing all the answers, and it is a distinction which is frequently lost in the media, because we look to say, oh well, we don't know anything, or this is the cast iron answer, and now we can all go home. And static electricity is a really nice example of something where the basic story is very well known. We know how it works for metals extremely well, except you never notice it in metals because they're such good conductors. But when it comes to sort of balloons and woolly jumpers and things like that, exactly which charges are moving is not clear. And it's got a lot to do with chemistry and the pressure of the two things you push together, and exactly what the humidity is. There's a lot. It's quite complicated, it turns out. The simple story is correct. We know the simple story. But the details are still being worked out. So, and I think the thing is that's just true for anything. There's always more subtleties along the line. That's just a particularly good one. But because of this real world thing, because there's lots of forces that are having very similar levels of importance in making things happen, almost anything you can apply that to, because there's always another layer.
I just had this argument earlier, and they said, well, we know how it works. And I said, well, tell me then. And
well,
they went,
So the question is, in order to know, that's a sort of a cultural language thing, isn't it? In order to know how it works, is that knowing enough to be able to make it happen again, or is that knowing every single thing about the entire system so you could model it on some kind of computer model, some sort of virtual world, and exactly the same answer would come out? Or is it knowing exactly, the probability distributions of the electrons around every single atom in the system? What does it mean to know something? How pragmatic are you? So the answer depends on your pragmatism level.
There's a little known experiment which is, I don't know if it's still being carried out at CERN, you probably know, is cloud.
Oh yeah.
Which is an experiment to work out how clouds form. Because that's not very well understood.
Thing, isn't it?
So you might think that everybody would know how clouds form, but it's really, obviously it's very, very important to understand. I mean, it completely affects the Earth's albedo, and it's a very complicated process. So they built like a chamber in which they tried to make clouds at CERN. So that's still going, that experiment?
And cloud physics is the biggest unknown in current climate models. And actually it's getting bigger as time goes on. The last IPCC report estimated our uncertainty about clouds as being bigger than the time before. You expect uncertainties to go down with time. Actually, it turned out to be one of those unknown unknowns where the door kept opening.
Next question. Whoever you can toss to. Nicely done.
Are we entering an era of anti-science, so the big questions won't even be asked? Silence. As in Trump and people having had enough of experts.
Well, yeah, that's slightly different than anti-science, I suppose, isn't it? Sort of anti-facts or anti-experts. we obviously definitely are in that arena, aren't we? I mean, I think it's very
well, maybe
clear.
they're just more vocal about it. It could be that people who've been excluded feel they can say so now, and maybe they always felt excluded. It's just that they believed the culture that said that they weren't supposed to know.
I think the idea that there's a process to securing reliable knowledge, and that can be quite hard work, and that you should keep your mouth shut until you've at least made some kind of a judgment about what the likelihood of what you're about to say is right or wrong. I think that is becoming unfashionable, less so than it was, say, 20 years ago. And so that was actually part of the motivation for why, Brian Cox and I wrote our latest book. So gratuitous plug for it. But that book is about how do you figure out reliable knowledge. So I think, so it is a proper answer to your question. It's not just a gratuitous plug of the book. It's the best thing that I can do is talk about it. Is talk about how you go about securing reliable knowledge, and hope that that it has some kind of an impact. And so that's tied in with just the joy of figuring things out. So ultimately it's connected with science education.
But there's two pillars of that, and I think this is something that those of us who talk about science in the public eye, don't acknowledge often enough, and I have been as guilty of it as anyone else, is that there are two equal pillars of science, right? There's the scientific method and all the ideas of exploring and finding things out in this free world where you're going to explore, and then there's all the things that have been found out using that. like I just said downstairs for anyone who's in the podcast session, the day we drop an apple and it goes up, we'll have a discussion about gravity. Until then, 9.81 meters per second squared, and it's going down. And there's these things that are sort of in this pillar of they've been tested over hundreds of years by thousands of people, and we haven't found a problem with them yet. So you can sort of rely on those, but then there's also this bit of science which is the method and the finding out and the questioning. And the questioning is obviously the important bit, but why start your questioning back at ground level when there's this enormous edifice of knowledge over here? And that's the bit where you start to sound snobbish as a scientist. We want people to explore and experiment and to understand the method, but then we're saying, oh, well, but people have already found these things out, and you can find them out again for yourself, but we sort of know the answer. And then there's these things where we don't know the answer yet, and they're in the middle. But they're equal. I think one of the problems of science education is that it was very on this side. Here are the facts, and you're going to learn the parts of a frog. There we go. And then recently it's become, oh, we should have methods and everyone should be able to think, and sort of peer learning thing, right? Which is fine, but why throw away all of what humanity has previously done? There's the understanding of the method, and then there's the where it takes you. So, and I think that we've still not got that balance right.
Yeah, I mean, there's an excitement about conspiracy, isn't there? There's a sort of this idea that there's an accepted opinion or an accepted set of, body of knowledge. It's actually sometimes more exciting to think that that's wrong and you're right. And I can't count the number of emails I get with Einstein was wrong, whatever. Those sorts of emails.
So was Einstein, isn't it? It's interesting. Nobody else was ever wrong, but Einstein was wrong all the time.
I don't know. We're all wrong as well, I guess, some of those emails. But that I think that's, in a sense, the internet sort of is amazing for disseminating and bringing people together and so on. But it also allows the construction of these sorts of conspiracies, these bodies of sort of. People can sort of feed off each other in that sense.
People never do that about aeroplanes, though, do they? Conspiracy theories that angels are flying underneath aeroplanes and carrying them along.
I don't know, maybe they do.
Chemtrails people have quite a lot to say about that, right?
Hey, this is a whole other panel. I'm afraid we're just about out of time. And anyway, the first mention of Trump, I've got to shut the session down. Thank you. Thank you, everyone. A huge round of applause for Tim O'Brien, Helen Czerski, and Jeff Forshaw.